The galaxy isn't just stars. It's full of hidden oceans. Under the ice of distant moons, there are seas. They're dark and they're churning. I want to talk about 20 of these worlds. 20 places where we could find life. One of them is a moon that shoots geysers into space. That might be our best chance to look. And then there are water worlds. Bigger than Earth, pitch black down there. What kind of life could swim in that? What does it even mean for a place like that to be alive? A habitable world. It's not about blue skies or green fields. Out here, it's a hidden recipe, conditions buried under an unbreachable crust of ice. To find it, we look for three things. First is liquid water. That's the one non-negotiable ingredient. Water is the universal workshop. It's the medium where the chemistry of life can actually happen. But a dark, frozen ocean is a dead ocean. It needs a power source. That's the second ingredient, energy. Far from the sun's warmth, this energy often comes from within. The gravitational pull of a giant planet, for instance, constantly squeezing and stretching a moon in its orbit. That friction, called tidal heating, can warm an entire world from the inside out. Or heat can rise from the slow decay of radioactive elements in a rocky core, a natural nuclear furnace. The final piece is chemistry, the right building blocks. Elements like carbon, nitrogen, phosphorus, the same fundamental pieces that make up every living thing we know. When these three come together, water, energy, and chemistry, a frozen shell becomes a lid. A lid on a simmering pot of possibility. This simple checklist is our map, and the first place we look is surprisingly close to home. Our solar system is a local laboratory. It has several of these hidden ocean worlds. Each one is a model of what might be possible. The moons of Jupiter and Saturn, they're not just barren rocks. They're complex worlds, and some of them are leaking. Europa, a moon of Jupiter, smooth and cracked. Its surface is a fractured shell of ice. That's a sign of the churning ocean underneath. Then Enceladus, a small, bright moon of Saturn. It screams with activity. It shoots these plumes of water vapor and ice crystals, hundreds of miles into space from its south pole. These aren't just spectacles, they're free samples. A spacecraft flying through could, in theory, taste the chemistry of that hidden sea. Ganymede and Callisto, also around Jupiter, they hold their oceans deeper. Locked under thicker ice, but they're there. And then Triton, Saturn's largest moon. It's a world unto itself, rivers and lakes, but not of water, of liquid methane and ethane. Yet beneath that frigid surface, scientists suspect a more familiar water ocean, a salty layer sandwiched between ice and rock. Even Neptune's moon Triton, with its bizarre backward orbit and icy volcanic activity, it's a candidate. These are our test cases. By studying them, we learn what to look for when our telescopes point at worlds light years away. They prove a point. A habitable world doesn't need to bask in a sun's golden light. It can be born from the warm, dark embrace of a planet's gravity, thriving in a permanent midnight that changes everything about where we think life could be. There's a global ocean under the ice on Europa. It's one of Jupiter's moons, and that ocean, it holds twice the water of all the oceans on Earth. The surface is this pale shell. Cracked, a jigsaw puzzle of shifting plates, long fractures everywhere, stained reddish-brown. It looks shattered, like it was broken and glued back together. Those cracks come from stress, from Jupiter's gravity pulling, squeezing, and from the other moons tugging too. That tidal heating, it generates warmth. Enough to keep that ocean from freezing. It's an engine, churning a dark sea against the ice ceiling. Hubble has seen plumes, water vapor erupting through the crust. A taste of what's underneath. That makes Europa a target. The Europa Clipper mission will fly by dozens of times. it'll analyze the plumes, that reddish material on the surface. Scientists think it could be salts, ocean salts coming up through the cracks. If the chemistry is right, the seafloor might be like ours. On Earth, hydrothermal vents on the ocean floor, mineral-rich water, heated by the core they support life. Entire ecosystems, no sunlight, just chemistry. So Europa's briny depths, could they have vents like that? And life around them, that possibility. That's why that cracked, frozen surface is a front door. One of the most compelling places we're looking. A sealed vault is hard to search. Europa gives hints, but the real breakthrough came from somewhere smaller. More explosive, Enceladus, a tiny moon of Saturn, only 300 miles across. Its surface is a brilliant white, like a mirror. It should be frozen. Silent, but it's not. From its south pole, enormous geysers erupt, blasting water and ice hundreds of miles into space. If Europa is a vault, Enceladus is an open book. And it's throwing its pages out for anyone to read. For over a decade, the Cassini spacecraft orbited Saturn. It made daring passes, flying right through those plumes. It didn't just take pictures, it tasted them. The data was clear. The plumes were mostly water vapor and ice, but mixed in were salts, like the salts in our oceans. It found simple organic molecules, the building blocks life uses, and then it found molecular hydrogen. That's a key detail. On Earth, around hydrothermal vents in the dark, certain microbes use hydrogen as an energy source. They combine it with carbon dioxide to live. Finding hydrogen in Enceladus's plumes suggests a similar reaction could be happening on its seafloor, a potential food source just sitting there in the plume. The picture that forms is of a world built for chemistry to become biology. Enceladus has a global ocean under an icy shell. That shell is thin and fractured at the South Pole, so the ocean vents straight into space. Below the water, scientists think the ocean touches a hot, rocky core. Saturn's gravity provides the heat, likely making hydrothermal systems on the seafloor. It creates a planet-sized mixing chamber. Warm, mineral-rich water from the rocks meets the cold ocean above. It swirls together all the ingredients: water, energy, complex chemistry in one place. For someone looking for life, that's the most promising cocktail in the solar system. It's all there, and it's being delivered to us free by those geysers. A future mission could fly through, collect a sample, analyze it with better instruments than Cassini had. We wouldn't need to land or drill. The moon does the hard work. This small, bright world, screaming its secrets into the void, might be where we find our first answer to the oldest question. Ganymede is huge. It's bigger than Mercury. Not just an ice ball, it has geology as complex as a planet's. There's an iron core deep inside that generates a magnetic field, like a small version of Earth's shield. And that field clashes with Jupiter's. It creates auroras, shimmering lights in a sky no one sees. The surface is old, cratered, but underneath there are layers. A rocky mantle, then an ocean, a colossal ocean, but it's not like Europa's. Europa's ocean is right up against the ice crust. Ganymede's is different. It's a deep, dark sea, trapped, sandwiched between a top layer of ice and a bottom layer of ice. A subterranean ocean in a frozen vise. The pressure is immense. The weight of hundreds of miles of ice pressing down. The temperature is above freezing because of internal heat, but it's still frigid, and it's pitch black. Forever dark, but the Hubble Space Telescope gave us a clue. Scientists watched Ganymede's auroras shift. From that, they deduced a salty layer under the ice. An electrically conductive layer. That layer is an ocean, and it holds more liquid water than all of Earth's oceans combined, all of it hidden in that dark, pressurized sandwich. So the question isn't just about water, it's about resilience. Could the chemistry of life begin there and persist in that confined, heavy darkness? Ganymede has no geysers like Enceladus, no surface cracks like Europa. It keeps its secrets locked tight. Studying it means listening to subtle whispers. The hum of its magnetic field, the slight wobble in its rotation. To understand the ocean churning far below, it represents a different kind of habitable world. If life exists there, it would be a prisoner of geology, surviving not in an open sea, but in a global aquifer. Under perpetual ice, it expands the blueprint. A living world doesn't need a surface. It doesn't even need a single, unified ocean. It might thrive in a vast, isolated chamber, a testament to life's tenacity. In the most secluded corners of a solar system, Callisto is the quiet one. The other moons, they have geysers, magnetic fields. Callisto just whispers. It's Jupiter's second largest moon, but it's the farthest out of the four big ones. Its surface is like a fossil, just ancient impacts, nothing like Europa or Ganymede where things get renewed. It's the most cratered object we know of in the whole solar system. That face, all battered, it tells you how still it's been. For 4.5 billion years, it's just been there. No volcanoes to repave it, no tectonics to wipe the scars away. This isn't a world of big changes. It's a monument to time, but under that silent, pockmarked crust, something might be moving. The Galileo spacecraft gave us a clue. When it flew by, Jupiter's magnetic field didn't tug on Callisto the way we thought it would. The best guess is a layer about 100 miles down that conducts electricity. A global ocean, salty. But if Callisto is so dead geologically, what keeps an ocean from freezing solid over all that time? The answer isn't the pull of the planet. It's in the rock itself, radioactive decay. Elements like potassium and uranium, they were trapped in Callisto's interior when it formed, and they slowly break down. That process releases heat. It's a gentle, persistent warmth from inside. Not a roaring tidal furnace, just a steady, low ember. Scientists think it might be just enough to maintain a liquid layer between two shells of ice. A dark, still sea, insulated by a thick ceiling of rock and frozen water. That changes the model. Callisto becomes a different kind of sanctuary. If that ocean is real, it's probably been liquid for the entire history of the solar system. A stable, unchanging environment, measured in billions of years, not millions. For life, time is a critical ingredient. Getting even the simplest organisms started is a slow dance of chemistry and chance. On a dynamic world, conditions come and go, but on Callisto they could persist, undisturbed for ages beyond comprehension. It teaches you something. Habitability isn't always a spectacle. It isn't only in the plumes of an active moon or the cracked ice of a stressed world. Sometimes it's a patient, silent whisper in the dark. A haven built not on ferocious energy but on profound, enduring patience. If life is in that ancient sea, it would be a different kind of resilience. The resilience of quiet constancy, holding a possibility aloft in the frozen dark for longer than life has existed here. Triton makes you question everything. It has rivers, it has lakes, there are shorelines, there are rain clouds, but that rain isn't water, it's liquid methane. It falls through this thick, orange haze. It lands on a surface of water ice, hard as stone, and this is the only other place we know besides Earth with that kind of active cycle, a liquid cycle. You're looking at a landscape that feels familiar, but it's built from entirely alien things. Then, beneath that surface, the story changes. Triton is massive. It has a rocky core, and the heat from its formation, from radioactive elements deep inside, that heat has likely created a second ocean, a hidden one. Not of methane, but of water, a salty sea rich with ammonia, trapped between layers of high-pressure ice far below those hydrocarbon lakes. So Triton isn't just one world. It's two potential habitats stacked on top of each other. The surface is a giant laboratory. It's for prebiotic chemistry. Those complex carbon molecules, the precursors to life, they're forming there right now. In the lakes, in the atmosphere, it's like a snapshot of an early Earth, but frozen at a much colder temperature. And you wonder, could those molecules, given time and the right conditions, could they assemble into something new? A form of life that breathes hydrogen instead of oxygen, that uses liquid methane the way our cells use water. Then you have the deep ocean, a warm, dark, watery environment. Not so different from what we think exists on Europa or Enceladus. It could have its own chemistry, its own energy sources coming from the rocky core. So could life exist there too, completely separate from anything on the surface, one world, but two completely independent recipes for existence. That duality is what makes Titan so important. It doesn't just add another candidate to the list, it shatters the list. It tells us that a single moon, a single planet, it can host multiple possibilities. Parallel possibilities for what life could be. The search isn't for a single answer anymore. It's for an entire spectrum of answers, just waiting in the dark. Some worlds you find them, but they weren't born there. Take Triton, Neptune's largest moon. It orbits backwards against the planet's spin. That's the mark of a capture. Triton is a visitor. It probably formed out in the Kuiper belt, that far-off disk of icy things beyond Neptune. A small, frozen dwarf planet just wandering. Then, in the ancient past, Neptune's gravity reached out and grabbed it, pulled this wanderer into a new, looping orbit, and in that process something happened. The moon came alive. When Voyager 2 flew past in 1989, it saw something unexpected. The surface wasn't static, wasn't just a cratered wasteland. It was dynamic. Geysers were erupting, plumes of dark material, probably dust, shooting miles up into a thin nitrogen atmosphere. They were driven by something under the ice. Distant sunlight warms dark surface material just enough, and it vaporizes pockets of nitrogen ice below. The pressure builds until it blasts through the crust, carrying that dark dust with it. This cryovolcanism, ice volcanism, it's a sign of internal energy. The capture by Neptune and the constant tug of its gravity would have stretched Triton's interior, heated it tremendously. That heat, maybe combined with warmth from radioactive decay in its rocky core, didn't just fade. It may have persisted, created a stable environment under the ice. So now scientists suspect, deep below those erupting plains of frozen nitrogen and water ice, there could be a subsurface ocean, liquid water, a relic ocean warmed by that ancient trauma of capture and maintained over billions of years. That changes Triton from a captured fossil into a potential sanctuary. It becomes a bridge, a direct link between the ocean moons we know around the giant planets and the countless, unseen dwarf planets and icy bodies still out in the Kuiper belt. If Triton, a captured object, can hold an ocean for so long, then many of its original neighbors out in the deep freeze might have similar hidden seas. The implication is staggering. The population of ocean worlds in our solar system alone could be far larger than we thought, with most of them silently orbiting in that perpetual twilight, far beyond Neptune. The journey goes beyond Neptune. It keeps going into the cold to Pluto, a dwarf planet with a heart. New Horizons flew past in 2015. What it sent back wasn't a dead world. It was complex, mountains of water ice, glaciers of frozen nitrogen, and that bright heart on its side, Sputnik Planitia. That heart is a clue. It's a massive impact basin. Smooth plains of nitrogen ice, but it's perfectly aligned, directly opposite the moon Charon. That alignment isn't random. It's like a weight. It shifted the entire world. The explanation is a subsurface ocean, a slushy mix of water and ammonia trapped between ice and rock. When the impact created Sputnik Planitia, it thinned the ice above this hidden sea. The dense liquid water beneath welled up. It created a gravitational anomaly, a heavy spot. Over time, Pluto rolled over. It reoriented itself to put that heavy spot facing Charon. The heart on the surface is a scar. It points to the ocean beneath. What keeps that ocean from freezing so far from the sun? The answer is a slow warmth. The gentle heat from radioactive decay, elements like potassium and uranium in Pluto's rocky core. It's a faint ember, but over billions of years, insulated by thick ice, it's enough. Enough to maintain a briny, slushy liquid, a dark sea in perpetual twilight. This changes the scale. If Pluto, a small, distant world, can hold a liquid ocean, then how many others can? Not just here, out there among the stars, the galaxy must be filled with icy dwarfs, planetesimals, rogue moons, each one a potential vessel for a hidden sea. The most common habitable environment might not be a warm planet like Earth. It might be a frozen shell with a heart of dark, patient water, beating slowly in the cold. Ceres doesn't match what you'd expect. It's out there in the asteroid belt, which you picture as just this field of dry, broken rock. But Ceres isn't just another rock. It's a world. Dawn showed us a surface full of mystery. Those bright spots in Archetypes crater, glaring out against all that gray, they're not sunlight on ice. They're salt, sodium carbonate, like something from a dried-up seabed, and they're fresh. This wasn't put down billions of years ago. It came up from below recently. In geologic terms, it was brought up by something liquid, so the story Dawn tells is about a hidden ocean, not a global sea like Europa has. Something maybe more interesting, a huge, regional reservoir of brine. A thick, salty sludge, rich in minerals trapped inside the rock. It stays liquid because of internal warmth from radioactive decay, the same gentle force we see on Pluto, on Callisto. Every so often, an impact shakes things or pressure builds down there, and this deep brine finds a way up. It reaches the cold, airless surface. The water just sublimates away into space. Leaves behind those bright, salty stains like a calling card, and that changes how we see where an ocean can be. Ceres doesn't have a giant planet nearby, squeezing it with tides. It's small, isolated, orbits in the freezing vacuum between Mars and Jupiter, but it holds onto its liquid. So the recipe for a subsurface ocean is more forgiving than we thought. It doesn't need a gravitational powerhouse. It just needs a little internal heat, the right chemistry, a thick enough shell to act as a lid. Ceres blurs the line completely. It's a protoplanet, a relic from the solar system's birth, and it's a contemporary ocean world. It proves liquid water isn't a privilege just for moons around giants. It can be a secret held by the smallest worlds, a quiet, enduring potential in the most unassuming places. If Ceres has this, then how many other asteroids? How many other frozen dwarfs holding similar secrets inside? The asteroid belt might not be a graveyard of stones. It could be a scattered archipelago of hidden seas. Our solar system is a neighborhood. The galaxy is a continent of stars, and many of those stars have planets. Exoplanets, we've found thousands. Some are gas giants, others are rock, but the most interesting ones might be water worlds. Finding an ocean that far away isn't about taking a picture. It's deduction, a detective story written in starlight. You start with a wobble. A star doesn't sit perfectly still. A planet's gravity tugs on it, creates a rhythmic shift in the star's light. From that wobble, you get the planet's mass. Then, if the planet passes in front of its star, you see a tiny dimming. The amount of light blocked tells you its size. Mass and size give you density, and density is a clue to what it's made of. A world with the density of rock, but much larger, could be rock and a huge amount of water. A water world, no continents, just a global ocean hundreds of miles deep, under a crushing atmosphere or a shell of high-pressure ice. Location is another clue. The habitable zone, that distance where a planet with the right atmosphere could have liquid water. Too close, the water boils. Too far, it freezes. But a planet in that zone is only a candidate. It means the temperature could be right, not that an ocean is there. The real evidence has to come from the air itself. That's the next frontier, analyzing the atmosphere of a distant world. When a planet transits its star, a tiny fraction of starlight filters through its atmosphere. Molecules in that air absorb specific colors. By splitting that light into a spectrum, astronomers look for fingerprints. The signature of water vapor would be a huge find, but water alone doesn't mean life, it just means water. More compelling would be a chemical disequilibrium. An atmosphere that shouldn't exist unless something is actively replenishing it, like oxygen alongside methane. On Earth, that combination is maintained by life. Finding it on an exoplanet would be the strongest hint yet of a living ocean below. So the search is a layered puzzle. Density suggests the possibility. Orbit suggests the potential, but the atmosphere holds the promise. We're learning to read the faintest whispers from unimaginable distances. Each candidate is a story pieced together from fragments of light. A narrative of inference that says another ocean might be waiting. Kepler 22b. That name changed things. Before that, the habitable zone was just a line on a chart. A theory, then we had an actual address. The Kepler telescope found it. A planet going around a sun like ours, but 600 light-years out. What made it matter was where it sat. Right in that Goldilocks zone, where temperatures could mean liquid water right on the surface. It was the first proof. Planets like that weren't just an idea. They existed. This world is bigger than ours, a super-Earth, 2.4 times the radius. We don't know what it's made of, rock, gas, something else. But a lot of the models point to one strange possibility. Kepler 22b could be a water world, not a moon with a hidden sea, a planet where the whole surface is an ocean. One single, unbroken ocean, an ocean that could be hundreds of miles deep. An abyss so huge our deepest trench would be like a puddle. Down at the bottom, the pressure, it wouldn't just be high. It would change things. It could force water molecules into exotic ice, hot ice, ice made just from pressure, forming a solid floor above the planet's rocky core. So the question changes. It's not just is there water, it's about an ocean that never ends. Could life start in a place like that, a planet-wide sea? No shores, no tides from a moon, no continents washing minerals into the water. The chemistry would be isolated, just what comes up from the seafloor or drifts down from the sky. But life finds a way. In our oceans, we have whole ecosystems at hydrothermal vents. Life in total darkness under huge pressure. A global ocean means a global seafloor. A whole planet's worth of potential vents, seeps, sources of chemical energy. This world changed how we think. It showed us a habitable zone planet might not be Earth-like. It might have no land, no mountains or beaches, just a deep, permanent global sea under a cloudy sky. It rewrote the blueprint for a living world. After that, looking up at the stars, we weren't just searching for pale blue dots anymore. We were looking for potential sapphires, whole worlds that might be gemstones of water, glinting out there, holding their secrets in the dark under all that pressure. The TRAPPIST-1 system is like a miniature solar system. A cool red dwarf star, not much bigger than Jupiter, holds 7 worlds. They're all roughly Earth-sized. They orbit so close together that from one you could see the others as distinct orbs in the sky, some larger than our moon. It's a compact family, and one stands out. TRAPPIST-1e, that planet sits in the star's habitable zone. Its density says it's likely rocky, but with a twist. That density is a little lower than pure rock. The best explanation is a significant amount of water. Not necessarily a global ocean, but a substantial reservoir. It could be surface oceans or vast ice over a hidden sea. The tight dance of these 7 planets creates a complex gravitational pull. They tug on each other constantly. that generates tidal forces, an internal friction that can heat a world from the inside. Even if the surface is frozen, that heat could maintain a liquid ocean beneath the ice. A dark, warm sanctuary shielded from the star's flares. Its true promise, though, is in its air. Because this entire compact system is relatively close, only about 40 light-years away, it's within reach of the James Webb Space Telescope. That telescope is designed to do something extraordinary. It can analyze the starlight that filters through the atmosphere of TRAPPIST-1e as the planet passes in front of its star, a breathalyzer test from across the galaxy. Scientists will look for the chemical fingerprint of water vapor. They'll search for hints of gases that shouldn't exist together naturally, like oxygen and methane. On Earth, that's a signature of life's activity. TRAPPIST-1e represents a new era. It's not a hypothetical world from a calculation. It's a specific Earth-sized target with a known address. We have its orbital period. We know when it will transit. We are poised to study its atmosphere in detail. It is the first world where we might move from asking if an ocean could be there to actually detecting the signs that one is. This one small planet in a tiny system around a faint star could become the most important world we've ever found beyond our sun, a test case for whether a compact, tidal-heated, water-rich world can truly be a home. Proxima Centauri b. It's the closest rocky planet we know of beyond our own solar system. It orbits the star nearest to our sun, and it's in that star's habitable zone. But that star is a red dwarf, small and cool, so for the planet to be warm enough, it has to orbit incredibly close, so close it's probably tidally locked. One face always turned toward its dim sun in permanent daylight, the other side in permanent night. A world divided. That setup suggests extremes, a blistering desert on one side, a global ice cap on the other. But an ocean changes that. A global sea could act as a heating and cooling system. Currents would carry warmth from the dayside around the globe and bring colder water back. So the most likely place for temperate conditions wouldn't be a broad continent. It would be a narrow band, the twilight zone where the sun forever sits on the horizon. There, with a moderating ocean, you could have stable liquid water, a ribbon of habitability circling the entire world. We don't know its true nature yet. Does it have that crucial ocean, a thick atmosphere to blanket it, a magnetic field to shield it from the star's radiation flares? We don't know, but its importance isn't just scientific. It's about distance. Proxima Centauri b is just over 4 light-years away. In galactic terms, that's next door. That proximity changes everything. It brings the dream of direct study from science fiction into the realm of possibility. Missions are being dreamed up, not just to observe it from afar, but to send tiny, fast probes there within a human lifetime, to fly by and maybe snap a picture. A glint of an alien ocean on the horizon. This world makes the search tangible. It's no longer an abstract dot of light in a catalogue. It has an address we all share. The closest possible place where another ocean might be waiting. It turns the grand question of life in the universe into a local question. What is happening right now on the world next door? TOI 700d is a quiet candidate. It was found by the TESS satellite orbiting a calm M-dwarf star. This star doesn't have the violent flares you see with so many red dwarfs. That stability is the first thing. A planet can hold onto its atmosphere over billions of years if the star isn't constantly blasting it away. The second thing is location. This world sits right in its star's conservative habitable zone, not just at the edge but the sweet spot, where liquid water could last on a rocky surface for a very long time. And the planet is small, roughly Earth-sized. That size matters. A world that size is much more likely to be rock and metal, like Earth, not gas. It has the right foundation. So you have a checklist almost complete: a stable, quiet star, a rocky planet, an orbit in the temperate zone. all the conditions are there for an Earth-like world. Climate model scientists have run show that with the right atmosphere, TOI 700d could have oceans, not hidden under ice but right on the surface. Glinting under an alien sun, it represents a shift. For years, the first exoplanets we found were giants, hot Jupiters, then we found super-Earths bigger than our world. But TOI 700d is a signal. It shows our technology is now sensitive enough to find the small ones, the quiet ones, the Earth-sized dots around small stars. It's a template. This is what we're looking for when we talk about Earth 2.0, not a perfect twin, but a world that ticks the most critical boxes. A place where the story of an ocean and maybe a biosphere could be written on the surface in the open. We don't know yet if it has that water, but it tells us where to look. And it proves such worlds aren't just fantasy. They're out there waiting in the data for us to find them. LHS 1140b is a super-Earth. It's very dense. Mostly rock and metal. The gravity would be crushing, and it probably has a massive iron core. But where it orbits is interesting. It's near what's called the snow line of its star. That's the distance where it gets cold enough for water to freeze into ice grains. That's the raw material for planets. So to find a world this dense out there in that ice zone is a puzzle. The main idea now is that it moved. It might have started farther out, a giant snowball of rock and ice. Then, in the early chaos, it migrated inward, drifted closer to its star, and as it moved into a warmer orbit, all that ancient ice would have melted, not just some of it, a cataclysm of melting. An entire world's worth of frozen water turning to liquid. What you'd get is a hybrid planet, a colossal rocky sphere with an iron heart wrapped in an ocean. An ocean hundreds of miles deep under a thick, steamy atmosphere. It's a world built in two stages, built in the cold, then transformed by a change of orbit. That challenges the old idea of where ocean worlds come from. We usually think they form with their water already there, or it gets delivered later by comets. But this planet suggests another path. A world can be born dry and rocky in the inner system, or icy in the outer darkness, and through a gravitational dance it finds a new location. And its very composition changes. Its ice becomes its ocean. This one planet expands the story of how a habitable environment gets made. It's not always stable or gentle. Sometimes it's a dramatic voyage, a planetary migration that turns a frozen relic into a water world. It means when we look at a planet's current orbit, we might only be seeing the final chapter of a much longer, more turbulent story. There's this planet K218b. It's not a rocky world. It's a mini Neptune, somewhere between Earth and Neptune in size. For a long time, we thought planets like that were just small gas giants. All atmosphere, no surface. Then Hubble looked. It studied the starlight passing through that planet's air. And it found water vapor, the atmosphere of a world over 200 light-years away, holding water. That fact changed everything. It turned a whole category of planets from curiosities into candidates. It gave rise to the Hycean world idea. Hycean, hydrogen and ocean. The idea is a planet with a huge hydrogen-rich atmosphere, like a mini Neptune. But underneath that deep, hot, pressurized air, there could be a global ocean. Not a cold sea under ice, a hot ocean maybe boiling under a permanent crushing fog. The surface would be unimaginable, no land, just a roiling sea under a sky so thick it blurs where the atmosphere ends and the ocean begins. The pressure at the ocean's surface would be immense, hundreds of times Earth's pressure, and the temperature could be in the hundreds of degrees. K218b itself is probably too hot for life. It orbits very close to its star, but the concept it proved is revolutionary. We can detect water in the atmospheres of these smaller gas planets, and if a Hycean world existed farther out in a cooler orbit, that steamy ocean could be temperate. Life there would follow completely different rules. It wouldn't breathe oxygen. It might metabolize chemicals from that hot sea, or use hydrogen from the atmosphere above. The whole planet would be one habitat from the deep ocean floor up into that soupy air. This redefines the habitable zone. Astronomers had mostly written off mini-Neptunes as uninhabitable gas balls. The Hycean hypothesis opens the door. A planet doesn't need a rocky surface or a thin atmosphere like Earth's. It can be shrouded in hydrogen and still have a vast global sea. That means thousands of already discovered exoplanets, ones we'd ignored in the search for life, suddenly come back into the conversation. It suggests a whole new class of ocean world might be the most common type in the galaxy. Not pale blue dots, shrouded sapphires, they're oceans hidden under a veil, waiting for us to learn how to see through the steam. The story goes beyond just a few named planets. It opens up into this whole range of possibilities. The last examples aren't just individual worlds, they're more like categories, archetypes. They show the incredible variety of how an ocean can even exist. Each one is a different answer to the same basic question of what makes a world alive. So first, there's the eyeball Earth, a planet locked to its star, one side always facing the light. On that day side, right under the constant sun, you could have a permanent ocean of liquid water, a single circular sea, like a planet's eye, but just past its edge the temperature falls. The ocean becomes a ring of ice, and then you get the permanent frozen night on the far side. Any life would be confined to that narrow band, that eternal twilight at the water's edge. It's a world of sharp borders where the habitable zone isn't a distance in space, it's a literal line on the ground. Then you have the super-Earth water worlds. Planets several times our mass with stronger gravity, thicker skies. Their key feature is depth, a global ocean not hundreds of miles deep but thousands. So deep that the pressure at the bottom creates exotic forms of ice. Hot ice, solid, forming a strange seafloor above the rock. These are planets of pure ocean. No continents, no beaches, just endless water under a cloudy sky. Any life there would be a creature of the deep, never knowing a surface that wasn't water. We can look beyond planets to their moons, the ice moon analogues. Picture a gas giant in another system with a family of moons. One of them, the right size and distance, gets squeezed by the planet's gravity. That tidal heating warms its core, melting a layer of ice into a global sea. It's like Europa or Enceladus, but in a solar system 1,000 light-years away. These hidden ocean worlds might be the most common habitats of all, orbiting countless giant planets we've already found. Some worlds are caught in the middle of changing. The evaporating sub-Neptunes, planets that started with thick, hydrogen-rich atmospheres, but they orbit too close to their hot, active stars. That atmosphere is being stripped away, blasted off by stellar radiation over billions of years. What's left behind as the gas shroud thins could be the rocky or icy core it always hid. A core that might now be exposed, still hot from its formation, possibly holding a vast magma ocean or a water ocean under a new, thinner sky. It's a planetary transformation seen in slow motion. Chemistry gives us even stranger seas. On a carbon planet where carbon is more abundant than oxygen, the rules are different. Water might be rare. Instead, the surface liquids could be hydrocarbons like the methane on Triton, but planet-wide, or other exotic solvents like liquid carbon dioxide under pressure. In an ocean like that, the chemistry for life would need a completely different set of blueprints, creating forms of biology we can barely imagine. And finally, there's the loneliest ocean. The rogue planet, a world ejected from its young star system, cast adrift into interstellar darkness. With no sun, its surface temperature drops near absolute zero. But inside, the heat from its birth and from radioactive decay remains. That internal warmth, trapped under an insulating shell of ice hundreds of miles thick, could maintain a subsurface ocean for billions of years. A dark, warm sea, traveling in perpetual night between the stars, life there would exist in total isolation. Its only energy would be the gentle heat from the planet's own heart, in an ocean with no surface, under a sky with no sun. This whole gallery shows that the potential for alien seas is limited by physics and chemistry, not by our Earth-centered imagination. When we ask if life is out there, we're not asking if there's another Earth. We're asking if any of these countless, varied possibilities has sparked into being. The answer is waiting in that dark water. Life in the dark. It starts with the chemistry of an alien ocean. On Earth, life adapts. We find microbes in boiling acid in deep sea trenches, miles underground under Antarctic ice. They don't just survive, they flourish. They use chemical energy where there's no light. They breathe iron or sulfur or methane. So if life can do that here with Earth's recipe, what could it do with a different set of ingredients? In a dark ocean like Europa's, warmed by tidal heat, the energy source wouldn't be sunlight. It would be chemistry. On the seafloor, where hot water vents from the rock, microbes could perform a simple trick. They might combine hydrogen with carbon dioxide to make methane and energy, or use sulfur compounds. Entire ecosystems could be built on these reactions, like at our own ocean vents. The creatures there might be strange, pale, and blind, sensing their world through pressure or chemical traces in the water. Now shift the chemistry. On a world with a hot ocean under a hydrogen atmosphere, life might metabolize hydrogen itself, using the gas from the sky as fuel, combining it with elements in the steamy sea. In a methane ocean like on Triton, life would need a solvent other than water. Its cellular structures might be built from molecules that stay flexible in the cold. Its genetic information might not be DNA, but another molecule stable in that frigid liquid. This leads to ideas. Could life be based on silicon instead of carbon? Carbon is fantastic for building complex molecules. Silicon is similar, but its bonds are weaker. In a cold, low-energy environment, maybe silicon-based chemistry could work over vast timescales. An ammonia ocean. Ammonia stays liquid at much colder temperatures. In that chilly solvent, biochemical reactions would be slow, but life might operate on a different clock, patient over millions of years. And the information itself. DNA is our blueprint, but it's just one solution. In a different chemical environment, another molecule might do the job better. Something more stable under high pressure or radiation. The fundamental processes metabolism, growth, reproduction, evolution might be universal, but the tools to accomplish them could be utterly alien. The true revolution wouldn't be finding giant space whales or intelligent civilizations. It would be finding a single, simple microbe, a cell alive in the darkness of Enceladus or in the deep brine of Ceres. That discovery would answer the profound question. It would prove the transition from chemistry to biology is not a rare, miraculous fluke limited to our world. It is a natural process, a cosmic imperative that happens where conditions are right. We would stop asking if we are alone and start asking what forms life can take. Our definition of a living world would expand to include every dark, churning ocean, and the universe would suddenly feel not emptier but infinitely more creative. Full of potential, life is a puzzle, and the pieces are scattered across the solar system and the stars. For the ocean moons in our own backyard, the approach is direct, but it has to be delicate. We send robotic explorers. The Europa Clipper mission is launching soon. It won't land on that cracked ice shell. It'll orbit Jupiter and make dozens of close flybys of Europa itself. Its instruments are like a doctor's toolkit for a distant world. It will map the ice shell in detail, measure the thickness, and most importantly, analyze the composition of those sporadic plumes. It's looking for more than just water vapor. It will search for complex organic molecules, the kind that form the backbone of proteins and cells. It might even detect simple amino acids, the building blocks of life as we know it. Finding those in the plume would be a thunderous clue. It would mean the ocean below isn't just a chemical soup. It's a workshop actively assembling life's raw materials. A future mission to Enceladus could go even further. Imagine a spacecraft designed to fly repeatedly through those towering geysers, collecting ice grains and vapor in a specialized capsule, then returning that cargo to Earth for the most sensitive analysis we can perform. We could look for lipids, the molecules that make cell membranes, or for isotopic ratios in the chemicals, a fingerprint that often gets altered by biological processes. The goal isn't to find a fish swimming by the camera. It's to find the undeniable chemical signature of a living process, even a microscopic one, in that ejected sea spray. For the oceans on worlds light years away, the approach is entirely different. We can't send a probe within any human time frame. Instead, we become cosmic eavesdroppers. We use telescopes not to see the planet's surface, but to dissect the faint light that passes through its atmosphere. The James Webb Space Telescope is our first powerful tool for this. When a planet transits its star, a tiny fraction of the starlight filters through the planet's air. Molecules in that atmosphere absorb specific colors. By breaking that light into a spectrum, scientists can read the barcode of an alien sky. They will hunt for the clear signature of water vapor, confirming a world rich with the solvent of life. But water alone isn't proof. The true target is a biosignature, a combination of gases that shouldn't coexist without something actively replenishing them. On Earth, our atmosphere has abundant oxygen alongside methane. Left alone, those two gases react and destroy each other. The only reason they're both present is that life, plants, algae, bacteria constantly pumps out oxygen, while other life produces methane. Finding that same unstable pairing in the air of an exoplanet would be the strongest hint imaginable of a living biosphere below. Future observatories will be designed specifically for this hunt. They will block out the blinding light of the parent star to directly image pale blue dots and analyze their light for these telltale signs. The search also stretches into more speculative territory. We might look for technosignatures, not signs of biology, but signs of technology. On a tidally locked exoplanet with a permanent night side, could we detect the glow of artificial city lights against the darkness? Could our telescopes spot the chemical fingerprints of industrial pollution in an exoplanet's atmosphere, a byproduct of a civilization's activity? These ideas sound like science fiction, but they are grounded in the same principle, looking for an imbalance for something that nature, left to its own devices, would not create. This grand endeavor connects a robot sampling ice grains near Saturn to a telescope collecting photons from a star hundreds of light years away. It's a multi-generational project spanning decades. It is driven by a simple curiosity. Are we the universe's only experiment in awareness, or is the dark water everywhere humming with its own quiet, alien song? The answer is no longer a matter of philosophy. It is a technical challenge, and we are building the tools to meet it. From these geysers, from these dark seas, we're getting a new map of the galaxy. Not a map of stars, not empty space, a map of potential, a map of hidden water, these 20 worlds, the erupting fountains of Enceladus, the steamy shrouds of those distant Hycean planets, their beacons. They're more than coordinates in a catalog, more than entries on a list. They're proof of something simple, a profound truth. The universe isn't a desert. It's an oceanographer's dream, countless vessels of liquid possibility. The ingredients for life: water, energy, chemistry. They aren't rare treasures. They are common construction materials scattered across the cosmos, assembled in the quiet abysses beneath ice and sky, and that changes the entire quest. Searching for life isn't about scanning the void for a needle in a haystack anymore. It's about learning to recognize the haystacks themselves, understanding which of these dark, churning environments has crossed that threshold. That subtle, miraculous line from complex chemistry to simple biology, the missions we plan, the telescopes we build, they aren't just tools of science. They're extensions of our curiosity, how we listen for a whisper in the cosmic dark to find even a single microbe, fragile, swimming in the brine of an alien sea. That would be a discovery that echoes through all of human history. It would answer the oldest question with a quiet, definitive yes. We would know beyond any doubt that life isn't a fluke. It's a natural process, a cosmic imperative, a story that begins wherever water, warmth, and chemistry meet in the dark, and Earth would transform in our understanding. It wouldn't be a singular sanctuary anymore. It would become one island in a vast and living archipelago, stretching across star systems, maybe even between the galaxies. The ocean calls from the stars. It speaks in the silent language of chemistry and gravity, in the slow churn of tidal heat, the faint absorption lines in a spectrum of starlight. Our task is to be brave enough to listen, patient enough to decipher, humble enough to understand that we're just beginning to hear the first notes of a symphony that's been playing for billions of years. In the dark water, everywhere, that journey through cosmic oceans, that's just the start. If those hidden seas, their possibilities, if that held you, I'd say subscribe. The channel is about going deeper, space's big mysteries, from the surfaces of distant worlds down to the basic questions, the questions of existence. I'd want to hear what you think. In the comments, tell me, what kind of alien life seems most plausible to you in those dark waters? Maybe it's a simple thing. A microbe, resilient, clinging to a vent on Europa's seafloor. Or maybe it's more, something more complex, pale, slow-moving in the pressure of a super-Earth ocean. Share your theories, the imaginative ones. This conversation, this shared curiosity, that's how we explore, together. When we look up at the night sky, we're not just seeing lights. We're looking at a galaxy that could be filled with hidden seas, each one a story, waiting, a quiet experiment in biology, unfolding in the dark. Thanks for watching. And keep looking up.